thank you to the organizers of this meeting for inviting me to give this talk. I'm going to give you a slightly different perspective from most of the other talks you've heard. It'll be quite related to what Shriyanand spoke about yesterday. I'm going to define cosmic dawn as redshift 14 because that is the redshift at which we have the highest confirmed spectroscopic redshift of a galaxy. And redshift 3 is just arbitrarily defined as cosmic noon. You can choose z of 2 or z of 1.5 if you wish. So if you look at JWST, the key thing to remember is that it allows us to probe the rest frame optical band between 400 and 800 nanometers at relatively high redshifts for the first time with HST-like resolution and even better sensitivity. So therefore, for the first time, we are able to trace the bulk of the stellar mass which lives in the older stellar population, which emits in optical and near infrared. We are able to probe that for the first time. Rest frame optical is also less affected by the presence of dust compared to the rest frame UV. And what it enables now is that the techniques and technologies that optical astronomers have used for 100 years in studies of local galaxies in the universe at redshift 0, these techniques can be now applied, directly applied at redshifts 3, 4, 5, 6. JWST has a number of instruments. There are 4 in number. NIRCam is the near infrared camera, which goes from 0.6 to 5 microns. Corresponding to that is the near spec, which is the spectrograph. It's a multi-object spectrograph. It can do 100 plus targets via microshutters. It spans this wavelength range, and using prism and grism, it has 3 different resolutions at which it can operate. There's also NIRIS, which allows you to do slitless spectroscopy in the near infrared. And for the mid infrared, it has a do-all instrument called MIRI, which operates over a fairly wide wavelength range and does both imaging and spectroscopy. If you're interested in rest frame optical lines, then H alpha will enter the MIRI band at redshifts greater than 7.5, and of course it's quite sensitive to warm dust emission. A number of surveys have been carried out, galaxy surveys have been carried out with JWST, and it is so sensitive that you can reach absolute apparent magnitudes, AB magnitudes of 30 in various fields, and this enables the detection of extremely faint, very high redshift galaxies. These are some of the surveys which have released data. There's a very short proprietary period for JWST data. So all of these surveys either have public data in some partially reduced form. Many of them have fully reduced data and catalogs, etc., which are publicly available. So over the last 3 or 4 years that JWST has been in operation, it's made a number of surprising discoveries. So the first thing it found is there were too many disk galaxies at high redshift. And you saw an example on Monday when Rashi spoke about the Alaknanda galaxy. And if you go and get integral field spectrum of those galaxies, you find that many of them are regular rotators. This was not expected. Then it also found too many massive galaxies, too many luminous galaxies, too many large galaxies, too many high metallicity galaxies, and also too many massive dusty galaxies, which is a class by themselves. We call them red monsters. In addition to this, it also found too many massive yet quiescent galaxies. So these are referred to as post-starburst galaxies. So these are galaxies that in a very short period of time not only have formed a very large number of stars, but have also gone quiet. So it's like they've created a lot of stars, but after that they begin to look like quiescent galaxies when seen. Then of course there are too many compact, massive dusty galaxies. This again turned out to be a new class of objects. These are the so-called little red dots, believed to be very compact AGN, and they're very dusty and so on. Lots of challenging problems that they pose. And then there are too many protoclusters also that are seen. I will not talk about the last bullet point, but I'll cover some of the others. So Rashi showed you Alaknanda on Monday. This is an even more surprising galaxy called the Big Wheel Galaxy, because it's in many respects like the Milky Way. It has the same diameter as the Milky Way. It has the same stellar mass as the Milky Way. It rotates like a disk, just like the Milky Way, at speeds comparable to the Milky Way. And the only difference is this particular object is at a redshift of 3.25 when the universe was only 2 gigayears old. It's, as I said, stellar mass and size indicate Milky Way-like properties, very, very clear spiral structure. The only major difference between this galaxy and the Milky Way is that this galaxy is at the moment, or when it, at that point, at that redshift, is forming stars at a rate about 30 times larger than the Milky Way, okay? So it's an exceptionally star-forming galaxy. It's also located in a fairly dense cosmic environment. So this seems to suggest that favorable conditions for large disk formation in dense environments in the early universe were present. But to me, to form a Milky Way-like galaxy, fully with spiral arms, bulge, disk, everything, rotating, and to do assemble 10 raised to 11 stellar masses within 2 gigayears is really, really difficult to explain. So in the early days, of course, JWST produced a lot of photometric candidates for high redshift galaxies. And typically, so there was a survey called SEERS, which found galaxies within this redshift range. And these candidates are typically very compact, mean median half-light radius of about half a kpc, and they're fairly UV bright, okay? And the UV luminosity function was also explored between redshift 11 and 9, and all of them seem to exceed the lambda CDM based predictions of galaxy formation. The possible implication was what you've heard already from several talks, that maybe there's a top heavy IMF, maybe there's extremely efficient star formation, but this star formation cannot be continuous. It has to be efficient, but it has to be in short-lived bursts. The dust levels have to be very low so that most of the UV photons can escape the galaxy. But it was also realized very early on that photometric redshifts can be quite unreliable. The little red dots, for example, were originally thought to be extremely low dust but extremely high redshift galaxies. Turned out they were not at redshift 15 but more like redshift 5 and much more dusty than thought. This is an example where you have photometric redshifts estimated for the same galaxy using a limited set of broadband filters on the left column, and here you have a much more densely sampled set of filters. These are the so-called medium band filters. And if you look at the redshift of this galaxy determining using this data and that data, the redshifts turn out to be very different. And the numbers here, there's also a spectroscopic redshift available, and it turns out that if you go from here to here, then many of the degeneracies, for example, there can be a drastic degeneracy of you mistake the Balmer and Lyman breaks. And here the photometric redshift, the spectroscopic redshift is 2.69. With this data, you get a redshift of 0.19, and with this data, you get a redshift of 2.71, which is quite close to the true value. So things can be drastically wrong, big mistakes could be made and were made in the early days. But now with this addition of medium band filters, the reliability of photometric redshifts has been greatly improved. But of course, the golden standard is spectroscopic redshifts. And now we have redshifts at 14 or so. This is a paper from last year by Carniani et al. In Nature, and they found two galaxies at redshifts around 14, and they show sharp Lyman alpha breaks and negligible emission lines, placing them at about 300 million years after the Big Bang. The brightest is very bright. It's also spatially resolved. And what they said is, say in the paper is something I've quoted, that the excess of luminous galaxies in the early universe cannot be entirely explained by accretion onto black holes. Okay, there has to be star formation, considerable star formation happening there, and therefore galaxy formation models will need to address the existence of such large and luminous galaxies so early in cosmic history. So these are the spectra of these two galaxies. You can see that sort of blue world of about 1.8 microns or so. There is the Gunn-Peterson trough. You can't see the galaxy at all, but once you go redward, you begin to see the galaxy, as you can see in all of these bands. The spectrum is exceptional. I mean, to get a spectrum of this quality at redshift 14 would have been unimaginable with any other telescope. But now with the prism mode of JWST in NIRSPEC, we are able to get these spectra. Not only that, we are able to follow up these galaxies with some other instruments. So ALMA is a very, very sensitive instrument, and in the far infrared, one of these two galaxies was detected in the O3 line at 88 micron, and that gave you a very precise redshift, which closely matched the break-based redshift that you had from JWST. And this galaxy was found to be surprisingly metal-rich, but it was extremely dust-poor. So it doesn't have dust, but it has some of the other metals in large quantities. You can also follow up this and other galaxies with the MIRI instrument on JWST, and there you can get H-alpha detection, and therefore a fairly solid redshift. The implications of these objects is that rest frame optical spectroscopy of Z greater than 10 galaxies is feasible with the JWST MIRI instrument. We see lots of rapid ISM enrichment and extreme conditions prevailing in high redshift galaxies. You also find what are called these red monsters. So in a paper in Nature, as part of the FRESCO survey, they found 36 dust obscured galaxies within this redshift range, and among these 3 have fairly high stellar masses, again above expectation. So many of these papers invoke extremely high star formation efficiencies. 50% of halo baryons in stars are getting 50% of the halo baryons are getting converted to stars. This is 2 to 3 times more efficient than even the most efficient conversion that you see in low Z galaxies. This is a result that I sincerely doubt. There is something funny going on here for sure. Because these objects by themselves are expected to contribute 70% of the cosmic star formation rate density at a redshift of 6, indicating that efficient dusty starbursts in the early universe were quite important as a source of ionizing photons. So this is an image of the 3 of these galaxies. As you can see, it's extremely bright in the reddest 4.44 micron filter, but if you go to shorter wavelength filters, the galaxy has completely disappeared, and here you can see a clear H-alpha detection of these objects. Then quiescent galaxies at high redshift. So Karnal in a paper found a galaxy, extremely quiescent galaxies at redshift 4.65, no emission galaxies, lots of absorption galaxies, lots of Balmer absorption lines indicating recent end of the starburst. And so now people have found more, 10 massive quiescent galaxies at a redshift of between 3 and 5. And again, these are 3 to 5 times higher than pre-JWST models predicted, indicating that massive galaxies formed and quenched very rapidly, at least in some parts of the universe. So this is that post-starburst galaxy that I was mentioning. This has a very, very blue UV continuum. The absorption lines are very, very clear, which means that although it has a blue continuum indicating a strongly star-forming galaxy, Star formation is actually recently quenched here, and that is why you are seeing a number of strong absorption lines over here. So again, strange, it built up enormous stellar mass in a very short period of time and then went all quiet all suddenly. So what is being increasingly invoked in order to explain the mismatch between the observed galaxy luminosity function and the prediction from models is what is called bursty star formation. And the idea here is that these galaxies are forming stars, but they are forming stars very efficiently, but only for a very short period of time. Then the star formation switches off. Then again it starts after a period of time. And this is what allows you, like I'll just focus on this luminosity function, and you can see this is at redshift 12 that the observed data, the points in gray are photometric redshift data, so you can ignore them for the moment, but there are spectroscopic redshift based data points, and you can see that the burst without dust gives you a fairly good approximation for the data points. So this again will need to be explained. I mean, it's easy to say that the star formation is bursty, but what is the physics that allows for this kind of star formation? Because we don't see it in the nearby universe. So there is some tension with galaxy formation models. So these early quenched galaxies, these ultramassive dusty systems at redshift 5, all of these appear to be in tension with simple models that have been tuned with HST data. And obviously galaxy formation models will need to be modified for these early epochs. So initially there was a lot of talk about new physics, but these were probably premature for the reasons that I tried to describe. So what are the present implications to cosmology? It's not as simple as altering some lambda CDM parameters, because if these lambda CDM parameters are consistent with the HST measured UV luminosity function at lower redshift. So just tweaking those parameters will not work. So now at the moment, purely astrophysical solutions, which means modifying galaxy formation models rather than the cosmology, seems to be the preferred solution. We are fortunate that the earlier abundance claims, like very large number of excess of galaxies, was overestimated. That has eased the tension, and lambda CDM may still be fine. JWST early galaxies may tighten constraints on reionization and dark matter. So this has implications to some of the theoretical work that's going on, and whether star formation can reionize early or limited small scale dark matter structures, those will be affected. So people working on H1, complementary H1 observations and studies, theoretical modeling, will need to take these JWST observations into account. There's lots of future surveys coming up, lots of data. At the moment, we have 25 galaxies with confirmed spectroscopic redshift greater than 10, all except one JWST discovered. That number will grow by an order of magnitude in a few years, couple of years. There's going to be lots of spectroscopic follow-up, and there's lots of beautiful synergies with ALMA and eventually with Roman and Euclid. And of course, as far as theory is concerned, we'll need improved simulations, better models to incorporate early star formation, the burstiness, the feedback and dust gas physics in order to correctly match the JWST data. I'll stop here and I'll leave you with my conclusions.
Thank you for very nice overview, Yogesh. So I have a question related to outflows. Do you see any signatures of outflows in these high redshift galaxies?
There have been a few observations of outflows. Are you talking about AGN-driven outflows?
Yes. I mean, the next question was related to AGN. Do you see the AGN in the...
So there have been a few observations of AGN-driven outflows at high redshift, say greater than 6. But remember, getting an IFU spectrum is fairly expensive. So we have lots of photometric data on JWST galaxies numbering in the millions. but the number of the spectroscopic observations are still in the thousands or tens of thousands. So I think it should be doable even with, there's lots of, forgot to mention that about 50,000 reduced spectra are publicly available now. And so people can create their own subsamples of, let's say, AGN and study, see if you can see outflows in those. Not all of them are MS, the multi-shutter array spectra. So you won't get IFU data, which is what you really need. Also, the resolution may be a problem. So if the outflows are happening on lens scales which are too small for JWST to probe, you won't see it.
Yeah, and when you say spectroscopic redshift confirmation, which resolution you use in NearSpec, for example?
It's mostly for the most distant galaxies, people operate in prism mode, which is that 100.
Okay.
And that is enough for you to see the Lyman break clearly.
But if you observe with the 3000 or 2700, you will not see any difference in the spectrum.
Very faint.
Very faint.
I mean,
Okay.
even with JWST, is very faint.
Right.
Yeah.
Thank you.
There was one somewhere. Yeah.
Hi, Yogesh. Thanks for the nice talk. I'm curious about what are the prospects of getting the dark matter masses or the dynamical masses for some of these galaxies. I know for G and Z11, people have got at least some points of the circular velocity,
Yes.
and that's at redshift whatever, 10, 11, whatever.
Yes.
But what about?
So I think we can now do it between redshifts 8 and 12 or 8 and 11. There we have sufficient numbers and the galaxies are sufficiently bright for effective, I mean significant signal to noise measurements. And I believe people are trying to do that already.
What instruments are they using?
JWST NearSpec, yeah. There's nothing else actually because like even at redshift 5, 6 and so on, with HST you see nothing, right? And, even with WIFC3 is not very sensitive. HST ACS which operates in the optical band is sensitive, but once your UV just flows across it, you don't see the galaxy at all. Even Alaknanda which he showed is only visible in JWST. It's not visible in HST.
So you showed in the beginning one galaxy at redshift 3 or so.
Yes.
So it looked like a face-on galaxy.
Yes.
So how do you get the rotational velocity of this one?
It's not fully face on, it's inclined at some 20-30 degrees or so. So you can therefore get significant, and it's rotating, the sort of inclination corrected speeds are 200 kilometers per second. So it is rotating like the Milky Way, but it is sufficiently inclined for you to get a reasonable measurement. You can assume a disk, and the disk is circular, so you measure the ellipticity of the galaxy, and as it becomes more and more tilted, you can get inclination.
Okay, I had a quick question about, you said we don't have to worry about the basic lambda CDM model right now with whatever astrophysics. So, but lambda CDM, there are two parts to it. One is the background model and the perturbed thing. Do we have the seeding mechanism is this Gaussian random field, right?
Yes.
Is that good enough, or is there something new that can be added there? Like, some things like many of people are talking about in terms of seeds for,
Yes.
dense
So I think
seeds
it's a
with,
bit premature in the sense that it is actually a bit premature for observers to make any strong claims. Because there are, I mean, I have shown you the sort of just the top high level picture or everything looks good kind of thing. But there are some worrying details in the observation which need to be figured out. So I think it's totally premature for when observers themselves are not trusting their observations fully. It's a bit premature for theorists to start working on the basis that the observations are very good. So they're very sensitive, but that doesn't mean that the numbers they're giving you are correct. So there's a difference between precision and accuracy.
Hear this.
So there's a difference between precision and accuracy. The numbers are very precise, but doesn't mean they're accurate.
Okay.
Okay, last question and then.
So the list of issues that you listed at some point in your slides, were all too much, the number counts were too much.
Yes.
So does that indicate something about the nature of how inference is being done?
What do you mean by that exactly?
What I mean is there is nothing which is lower than expected, right? Everything is above the numbers that are expected.
Yes.
So that would mean that maybe some way of counting cutoff is too.
There could be, but people have tried to see what's happening. There is one trivial thing which some of the earlier papers didn't look at, which is there were predictions of how many galaxies it will see per square arc minute. Okay, but these were based on the nominal sensitivities of JWST. So on one of my later slides, I have a thing. This is a very trivial thing. JWST turned out to be 20% more sensitive than what people was the design value. So you just found more and more fainter galaxies, and you also said there are more galaxies than we expected. That's not correct because people were comparing the theoretical numbers. So there are many factors that have to be taken into account. But certainly one thing is true. One is going towards more galaxies at high mass, more galaxies at low mass, more AGN, more rapid growth of black holes, more rapid star formation. There's nothing which is less.